So this is it. This is part 3 of part C of chapter 2. This is going to bring everything home, and I'm going to integrate cardiovascular physiology. First of all, I'm going to bring together the Frank-Starling curve and the Sagawa pressure-volume relationship that we just talked about in cardiac physiology in the last section. And then with that, I'm going to totally bring together section 1 and 2, that is bringing together the Frank-Starling curve and the Guyton venous return curve. And this is really a graphical analysis that Arthur Guyton gave us to help represent the integration of cardiac function and venous return. And then finally what I'm going to do is I'm going to really bring together the Guyton analysis and chapter 1, which is the Campbell diagram, to really bring out or illustrate a full graphical representation of heart-lung physiology. And I predict that I'm going to knock your socks off. All right, so the Sagawa pressure volume curve and the cardiac function curve. So if you're just tuning into part 3, go back and watch part 2, or else this isn't going to make much sense. But as I introduced in the last portion, the cardiac function curve, the cardiac response curve, or the Frank-Starling curve, analyzes cardiac function in terms of right atrial filling, which is a surrogate for stretch, and bulk flow. That is, you fill the heart to this much, you get this much output. So there's really a clear relationship between the Sagawa pressure-volume relationship, and the Sagawa pressure-volume relationship really looks at the stroke volume, so it's kind of like quote-unquote cardiac output on a beat-to-beat basis versus the bulk flow of the Frank-Starling curve. And that's because the Sagawa pressure-volume relationship is a graphical depiction of stroke volume, and stroke volume times heart rate gives you cardiac output, which is what the Frank-Starling curve gives us. And so inspection of these two relationships can really be brought together, and what I want to do is show you this in a slide in a moment. And I want to show you that the cardiac function curve, the Starling curve, shifts up and down in response to various cardiac pathophysiologies, not just contractile state. And then just to reiterate that, in Chapter 8 of his 1973 textbook, the late Dr. Guyton described the cardiac function curve. He actually described it as the cardiac response curve as, quote, a composite function curve for the entire segment of the circulatory system between the input of the heart and its output, including, of course, both sides of the heart as well as the pulmonary circulatory system. So the slope of the cardiac response curve does not simply reflect its contractile state. So let's look at them side by side, and I've tried to color code these to make it visually pleasing and educational at the same time. So this is the Sagawa pressure-volume relationship that we just went through, including the arterial elastance, which illustrates ventricular-vascular coupling here, the end-diastolic pressure-volume relationship, the end-systolic pressure-volume relationship, and the stroke volume, which is the difference between the two. So this is your key to happiness right here. This is your cardiac filling pressure. Remember here, its filling pressure is on the y-axis and volume is on the x-axis. So this is your filling pressure, which is really what the filling pressure on the Guyton curve is your right atrial pressure at end diastole. And then the relationship between stroke volume and cardiac output I've illustrated in green. Remember, stroke volume times heart rate is your cardiac output, which is on the y-axis here, and so I've illustrated that in green too. So you can start to already appreciate the relationships here. So let's talk about systolic dysfunction, which we already talked about in section 2. So that's a down and to the right shift of your end systolic pressure volume relationship. Conversely, you can say this could be a valvulopathy, like a mitral valve regurgitation as well, would depict the same physiology. But what happens here is you then begin to fill at a higher pressure at a lower stroke volume. So higher pressure, lower stroke volume, how does that graphically represent itself here? Well, higher pressure, lower output, shift down into the right of the curve. I think we all appreciate that. Well, what about a really high afterload or an increased impedance? So say a hypertensive emergency. Well, On the Sagawa curve, on a beat-to-beat basis, that's depicted by a very high arterial elastance, so that the the impedance to flow in the arterial bed is very high. And so how does that depict itself on the Sagawa curve? Well, again, higher filling volume, the same or lower stroke volume will do just the same as the last. It will fill at a higher volume, and even if this cardiac output was the same, you tend to have a down and to the right shift of your Frank-Starling curve. And how about diastolic dysfunction? Well, that's a shift up and to the left of the end diastolic pressure-volume relationship, and I think you probably know where I'm going here, but you're going to fill at a higher pressure, and even if you have the same stroke volume, you're going to have a tendency to shift your cardiac response curve or your cardiac function curve down and to the right. So that being said, the cardiac function curve in all its glory, the x-intercept, I talked a little bit about this in part 2 of this chapter, but just to reiterate, because it's very important for what I'm about to talk about next, is that this is a representation of intrathoracic pressure, and that is if you were to uncouple cardiac output from venous return, so experimentally you'd clamp the IVCs and then measure the right atrial pressure, well, it would be equivalent, because the right atrium is a thin-walled, very compliant structure, it would be equivalent to the intrathoracic pressure, which is subatmospheric. So this intercept is critical to understand heart-lung interaction, because as you'll see, the two key mechanical mediators of heart-lung interaction is changes in pleural pressure or intrathoracic pressure and changes in lung volume. And as you'll see beyond that, that's very nicely represented, or as you saw in Chapter 1, very nicely represented by the Campbell diagram. So must understand this. If you don't, I don't know, just give up. So this is overall pump function, the slope of this curve, as we just went through in almost agonizing detail, that the shift of the slope of this curve describes the overall pump function and is mediated by changes in valve function, afterload, contractile state. And then the flat portion of the cardiac response curve really represents pericardial constraint, but it also represents mediastinal constraint, and as well the ventricles kind of have a cytoskeleton that prevent it from becoming distended or really rupturing. And so I frequently hear people say, oh, well, the patient, is overloaded and they've fallen on the descending limb of their Starling curve. Well, if this is the Starling curve, there is no descending limb. It's not like your pressure goes up, your pressure goes up, your pressure goes up, and then your blood flow starts to go down, your cardiac output starts to go down. That certainly occurs with a single muscle fiber. If you were to take a frog gastrocnemius muscle and stretch it and plot twitch versus stretch, you do get to a point where, and I think it's like a little over 2 microns or something, where as you stretch it beyond that, you get less twitch. But that's a single muscle fiber. That doesn't really happen in vivo, where you have a very complicated 3-dimensional ventricular structure with interwoven myocytes and cardiac cytoskeleton. And stop saying that. It drives me crazy. There's no descending portion. All right, so what did Arthur Guyton give us? Well, he took the Frank-Starling curve and then he matched it with his venous return curve, and he said, well, this is what determines your right atrial pressure. It's not just cardiac physiology, it's venous return physiology, and it's the combination of the two. So, as I talked about in the first portion of this chapter, you can increase circuit function by shifting the venous return curve rightwards, so you've increased your mean systemic pressure from here to here. And you can see what that does is it increases your right atrial pressure, compared to this as the resting state, but increases your cardiac output as well. And so this would be like fluid loading the patient, and I think this intuitively makes sense for all of us, that increasing the right atrial pressure here would increase the cardiac output. While a decrease in circuit function, so a decrease in the mean systemic pressure, so this patient, say, has bled out, they've decreased their stress volume, all the different causes of dropping your mean systemic pressure, as I talked about in the first part, you lower your right atrial pressure relative to the resting state, and you lower your cardiac output. So this patient has less venous return. Their cardiac function, their cardiac state, for illustrative purposes, has stayed completely static. It hasn't shifted up and to the left. And in actuality, if you were to bleed a patient out and shift their curve leftwards like this, they'd have an adrenergic response, which would then recruit some unstressed volume, shift this curve back to the right a little bit, and then certainly the adrenergic tone would shift the cardiac function curve up and to the left a little bit and try and defend the drop in cardiac output that you would get with a pure drop in your venous return. But it's very important to note that look how close this is to maximal venous return. Remember, the maximal venous return here and the essentially pericardial constraint, or the plateau of the cardiac output, these define your speed limits or your maximal cardiac output. So in this patient here, if I were to just flog them with epinephrine and shift this cardiac function curve up and to the left and shift it out this way, well, you can it's like flogging a dead horse. You could hit their myocardium with all the epinephrine in the world. You're not going to augment their output, because the rate limiting step here is that maximal venous flow has been reached. So that's why in said patient you would have to, if they'd bled out, we'll give them some blood and shift their curve back rightwards and improve their cardiac output that way. So let's talk a little bit about changing the cardiac function curve. So a shift up and to the left of the cardiac function curve represents an increase in cardiac function. So what that does is that tends to favor a lowering or a diminution of right atrial pressure, but an increase in cardiac output. So you can see that it's not purely a Starling mechanism here, because the Starling mechanism is that you increase right atrial pressure, you increase cardiac output. But here you've decreased right atrial pressure compared to the resting state, and you've increased cardiac output. And that's because you've shifted the cardiac function curve leftwards along the venous return curve. Similarly, a decrease in cardiac function shifts the curve down and to the right, which tends to, for a given venous return, tends to increase your right atrial pressure compared to the resting state and lower your cardiac output compared to your resting state. And this point here, this intersection of cardiac function and venous return function, is sometimes referred to as the operating point of the cardiovascular system, and it defines your cardiac output for your given right atrial pressure. And I think you can appreciate this is an incredibly dynamic number. So you're measuring this as somebody's CVP, and you're doing all these things to them, and this CVP is going to change very dramatically, and it will change in response to changes in cardiac function, in response to inotropes and vasopressors and fluid loading and afterload reduction. All of these things are going to change your right atrial pressure. So it's a moving target and quite dynamic. And it's not just due to changes in volume status, as I talk extensively about in Chapter 6. It's multiple variables are changing your right atrial pressure and therefore your CVP. And so I think you can appreciate if both curves change position, which frequently occurs in the ICU. In fact, it's hard for me to imagine a clinical scenario where only one of these curves is changing. Now imagine shifting the cardiac function curve up and to the left and the venous return curve to the right. Well, you've augmented your cardiac output compared to the resting state, but you actually may not even change the right atrial pressure or the CVP at all. And again, if you're more interested in this physiology, please tune into Chapter 6, because I go through much more detail what the determinants of central venous volume and central venous pressure are. And I use these curves as a model. So again, just to reiterate, the assessment of right atrial pressure or the CVP must always occur with consideration of both the circuit function and the cardiac function. And knowing the right atrial pressure is like knowing the arterial pH. It's almost completely meaningless without knowing the other variables that go into its determination. I hope that with this you can appreciate that trying to get somebody's volume status from their CVP is completely flawed and frankly ignorant. All right, so what happens with respiration? Well, I kind of talked about it already. Remember, this is the x-intercept, and this is what tracks intrathoracic pressure. So if you were to decrease intrathoracic pressure, say by taking a spontaneous breath, you actually shift the cardiac function curve leftwards in relationship to the venous return curve, comme ça. And so in this situation, you've lowered your right atrial pressure as a response to lowering the intrathoracic pressure, but you've increased your cardiac output. And this, I see sometimes medical students kind of scratching their heads on rounds saying, well, how is the right atrial pressure going down but the cardiac output going up? It doesn't make sense. And it doesn't make sense because you're just thinking of the world in terms of Frank Starling, and it's not just Frank Starling. That it is completely physiologically appropriate to increase your cardiac output in the situation where your right atrial pressure is decreasing, and that's exactly what occurs during a spontaneous inspiration. So this is effectively like a fluid bolus as you're shifting the cardiac function curve leftwards. It's kind of like shifting the venous return curve rightwards, which is like an increase in circuit function. And then what I've illustrated here is an important concept, and that is the transmural pressure. So the transmural pressure is the pressure within the blood vessel, say the IVC or the right atrium or the right ventricle or whatever you want it to be. It's the pressure within a distensible vascular structure. Within it, less the ambient pressure. And because this is tracking the ambient intrathoracic pressure and this is your intravascular pressure here, the transmural pressure is actually increased in this patient. So this explains why when you inspire, your right atrium tends to distend, your right ventricle tends to distend, even though it paradoxically doesn't seem to make sense, because how's your right atrial pressure going down yet your vascular structure distending? And it's because your transmural pressure is increasing. And I get a question a lot, like how does I'm so confused how an inspiratory event affects your right atrial pressure, and this curve really explains everything, that a change in your right atrial pressure in response to a change in intrathoracic pressure is dependent not only on the change in intrathoracic pressure, which is your x-intercept here, which is obviously profoundly affected by respiratory mechanics, but not just the change in intrathoracic pressure, but also the slope of your cardiac output curve, your cardiac response curve, which, as we talked about in section 2 of this chapter, is mediated by multiple variables. And then the right atrial pressure in response to a decrease in intrathoracic pressure will also be modulated by your venous return curve, your circuit function, which, as we talked about in section 1 of this chapter, is modulated by multiple variables. So as you can see from this simple analogy, or the simple illustration, that a decrease in intrathoracic pressure, its effect on right atrial pressure, is dependent not only on the change in intrathoracic pressure, but your cardiac function curve and all of its determinants, and your venous return curve and all of its determinants. So it's far from straightforward. So this is the transmural pressure, as I talked about. Transmural pressure is a static pressure, as I talked about on the first slide of the first part of this lecture. And as the transmural pressure increases, it tends to increase the volume of that distensible object, and that's mediated, and the degree to which the volume increases is mediated by compliance. So what happens if you increase intrathoracic pressure, like a Valsalva or auto PEEP? Well, again, you're following intrathoracic pressure here on your x-intercept, so you're shifting your curve rightwards, and what you've done is you've now increased your right atrial pressure as a function of your venous return, the increase in intrathoracic pressure, and your cardiac response curve. And you've decreased your transmural pressure, so you've actually tended to shrink the right atrium and the right ventricle. And again, this explains a somewhat paradoxical increase in right atrial pressure with a decrease in cardiac output. Again, like I see these medical students, just their heads are exploding. I don't understand. The right atrial pressure is going up, but cardiac output's going down. It doesn't make sense that right atrial pressure goes up, cardiac output's supposed to go up, and it certainly does. But that's only half of the picture. That's you're just thinking in terms of like 1870s physiology, and you have to understand that cardiac output is mediated by both the cardiac function curve and the venous return curve. Okay, so this is gangbusters. So I wanted to represent heart-lung interaction And as we saw in that previous slide, that the cardiac function curve and really the venous return curve also shifts in response to changes in intrathoracic pressure. Well, how to change what determines changes in intrathoracic pressure? Well, go back to Chapter 1 and look at the Campbell diagram, because that very nicely depicts how intrathoracic pressure changes in response to various pulmonary and chest wall pathologies. The static and dynamic properties of the respiratory system, as I describe ad nauseum in Chapter 1. And as I mentioned, the movement of the cardiac function curve along the x-axis follows the changes in the intrathoracic pressure during respiration. And therefore, a three-dimensional analysis of intrathoracic pressure to cardiac output can be made. So if you keep the Guyton analysis on the XY axis and you put the Campbell diagram on the XZ axis, which is directed into the page, you get it. And this is what you get. Hold on. I prepared for this. Pretty serious. Drop the Campbell diagram to the Z-axis, keep the Guyton analysis on the XY axis, and now you, my friend, have a very powerful tool in your mind, and that is how changes in intrathoracic pressure as a consequence of changes in lung elastance, which is a common pathophysiological problem in the ICU, changes in airway dynamics, which is a common pathophysiological process in the ICU, and changes in chest wall elastance affect changes in intrathoracic pressure on the x-axis, which then can be tracked by the cardiac output curve, as we just saw in those previous slides. So you can start to see how changes in right atrial pressure, cardiac output, begin to change in response to pulmonary disease. So the x-axis remains pressure, but I've changed its units for consistency to millimeters of mercury, because we're always measuring that darn CVP, and you got to understand where it comes from. And the new z-axis into the screen is thoracic volume via the Campbell diagram, and changes in pressure as a function of, as I mentioned, lung and chest wall characteristic represent the changes in the pleural pressure or the intrathoracic pressure. And the changes in pressure as a function of that's not very well written. I apologize. The intersection of venous return and cardiac function represents or determines your right atrial pressure. So heart-lung interaction in a nutshell. This is what we just saw. So let's go through a normal inspiration in a normal human being with a normal dynamic pulmonary properties, normal static pulmonary properties, and normal chest wall properties. So this, as you remember for Chapter 1, is FRC, and that's this thoracic volume on the z-axis here, and this intrathoracic pressure, which is slightly subatmospheric, and we know that from Chapter 1 because there's this kind of push-pull phenomenon between the chest wall trying to pull towards its equilibrium volume and the lungs trying to pull down towards its equilibrium volume, so it creates a mild vacuum in the intrathoracic space. This is your right atrial pressure. It's the crossroads of venous return, systemic venous return, and your cardiac output. This is your intrathoracic pressure, as I mentioned, at end expiration, and the difference between these two is your transmural pressure. So let's take a nice little deep breath in. You're going to move from FRC up to your new tidal volume. You're going to drop your intrathoracic pressure, comme ça. The cardiac function curve will trace this decrease in intrathoracic pressure, like we just saw. And now your right atrial pressure has decreased, okay, close to atmospheric pressure in response to the decrease in intrathoracic pressure, and your cardiac output has increased. And for simplicity, what I've left out is that, and I talked about this a little bit more in the first section of this Chapter 2, is that as lung volume increases, as the diaphragm descends, you actually tend to shift your mean systemic pressure out rightwards a little bit and increase your venous return somewhat. And And so even in a very simple normal inspiration, the change in right atrial pressure is dependent upon multiple variables. And you can start to imagine how changes in pulmonary physiology occur with various diseases, various chest wall disorders, various cardiac disorders, and disorders of venous return can in very complicated manners start to cause changes in right atrial pressure and cardiac output that can be difficult to predict. And what I hope that this graphical analysis gives you is a tool for a qualitative analysis. This is by no means can ever be a quantitative analysis, but you've got to understand that this is the physiology that's going on in the chest, and this is a normal patient. And in Chapter 3, we'll go through a little bit more in detail some of these interactions in the healthy patient. And then in Chapter 4, we're going to get into the nuts and bolts of various disease states and how all of these curves change. And I've spent a lot of time on these curves. So please tune in, humor me, spark your interest, fan the flames of your love for heart-lung interaction. Stay tuned. I'm going to take you on this ride. You're not going to regret it. Thanks again. Check out my website all the time. Tell your friends. Tell your wife. Tell your kids. Tell your children. Thank you and good night.